Good morning, good afternoon, good evening, wherever you might join us. And I'm glad to see freshly masked faces in Providence, some stuffing with some breakfast, others without. So glad to be back. So this is day 2 really of FLUOROS. Second try. Try this again. So good morning, good afternoon, good evening, wherever you might join us. I'm glad to see freshly masked faces in Providence, some stuffing their faces, others the masks. So welcome back. Glad to see everybody. A few quick reminders. This is still Rhode Island, so be aware where the fire exits are. Nothing funny about it. You can ask the locals why we have this rule. Second, code of conduct. It's included in all the materials. Be professional, respect boundaries, behave responsibly. The rules are recorded, it's URI copyright, speakers' reviews are their own and not SRPs or NIEHSs. Everything is on the Hoover mobile app for the next 3 months, and please look at the e-posters that are also online. As you're fully aware, if you're within the facility of water fire, please wear a mask unless you're eating. We try again to have dinner outside. Let's see if the skies cooperate today. And otherwise, do make use of being social at some mask-to-mask distance. Thank you. All right, again, we gather today on the traditional land of the Mashpee, Niantic, and Narragansett tribal nations. We honor their histories, ancestors, and perseverance in our communities today, as our country was built on indigenous land. We acknowledge the indigenous people and honor their stewardship of the land, sea, and resources that they hold sacred and that we shepherd together. So, and with that, we say coup de poutage.
Thank you, Rainer. So, I will be the moderator for the morning session today, and before starting that, it gives me a great pleasure to introduce to you our first in-person speaker, Emily Donovan. Emily is co-founder of Clean Cape Fear, a grassroots community group which formed in 2017 after learning DuPont Commerce spent nearly 40 years releasing large quantities of PFAS into the drinking water supply used by over 300,000 North Carolina residents and contaminated over 4,500 private wells. Her work has helped elevate North Carolina PFAS contamination crisis to the national stage. She has testified before Congress twice regarding PFAS contamination. She created a lobby day effort in Washington, D.C. for local community members to participate in a Washington Post live panel discussion with actor Mark Ruffalo and lawyer Rob Bellot. She helped organize and co-host 2 screenings of the movie Dark Waters in Wilmington and Raleigh, featuring special guest Mark Ruffalo. Both events resulted in North Carolina's Attorney General suing DuPont Commerce for natural resources damage, and North Carolina's General Assembly filing a historic amount of PFAS bill during 2021 and 2022 legislative session. Recently, Emily helped secure reverse osmosis filling station for 49 public schools impacted by PFAS contamination in Brunswick and New Hanover counties. She's a member of the leadership team of the National PFAS Contamination Coalition and sits on various community advisory boards and coalitions working to address PFAS contamination. It is with great honor to welcome Emily Donovan here this morning.
Thank you so much for having me. I'm here today to remind everyone attending this conference that what you do this week, what you share, what you learn, and how you apply it has an impact on me, my family, my friends and neighbors, and every other community like mine around the globe dealing with PFAS contamination. Clean Cape Fear is a grassroots organization, meaning we're not a nonprofit or paid advocates. We are residents living in an active contamination zone. We formed 4.5 years ago with a primary focus to build public awareness and seek accountability around PFAS uses and contamination. We are based out of the Wilmington, North Carolina area, and in June of 2017, we woke up one day to front page headlines stating the same thing DuPont did in Parkersburg, West Virginia with PFOA was the same thing DuPont, now Chemours, was doing with PFOA's replacement Gen X in southeastern North Carolina. We would later learn the situation was much worse than what we originally thought. We first learned about Gen X when a local news reporter discovered a scientific paper published 6 months earlier about PFAS chemicals in Wilmington residents' tap water. We felt angry, worried, and betrayed. Wilmington's water district knew about the study's findings for a full year and failed to alert the public. We attended protests and rallies, and when public leaders were afraid to give us answers, we organized the first ever public forums on Gen X. We brought lead scientists and community stakeholders to Wilmington to speak openly and honestly to the public about our PFAS contamination crisis. Let's take a closer look at what initially happened in North Carolina. NC State University researchers detected high levels of PFAS compounds in the Cape Fear River and the tap water of Wilmington's water district. In May of 2016, the US EPA revised their lifetime health advisory for PFOA and PFOS, lowering it to 70 parts per trillion. This triggered NC State scientists to notify Wilmington's water district of their Gen X findings in May of 2016. The researchers quickly published their findings that November, even though their labs were still working to identify the other PFAS detected in their samples. For a full year, Wilmington's water district failed to publicly respond to this information because there were no federally enforceable regulations for Gen X and the other PFAS detected. A local reporter who does not regularly cover environmental news got bored one day and decided to check scientific journals for anything interesting in his reporting area. He discovered the Sun et al. Paper and published its findings in June of 2017. This news story is how the public became fully aware of the PFAS contamination crisis in North Carolina. North Carolina is a significant state. We have a population of 10.5 million residents, making us the 9th largest state in terms of population. We are headquarters to some of the nation's leading environmental and health agencies. The National Institute of Environmental Health Sciences is headquartered in North Carolina, along with the US EPA's Research Triangle Park. RTP houses 15 US EPA agencies, including headquarters for the EPA's Air Pollution Research and Regulation Division, which I personally find ironic when we consider EPA's Air Pollution Division is less than a 2-hour drive from what many consider to be one of the world's most notorious PFAS air polluters. How did this get missed? I don't have an answer, but I do have a story to tell. The Cape Fear River Basin is the largest river system in North Carolina. Over 1.5 million residents rely on this river as their primary source of drinking water. It's also one of the nation's most PFAS polluted rivers. Residents in Pittsboro, North Carolina have some of the nation's highest levels of PFAS contamination in their municipal tap water due to upstream industrial discharges from unknown companies who use PFAS in their manufacturing processes and release their waste into the local sewer systems. If you move further downstream to Fayetteville, there are over 5,000 homeowners and counting struggling with private well contamination from PFAS air releases due to decades of irresponsible manufacturing practices from a single source polluter, DuPont, and later Chemours. We still don't know how many private wells are impacted because Chemours has not finished their court-ordered sampling program. A recent report showed the contamination extends at least 18 miles from Chemours and tends to follow historic wind pattern data. Every dot on that map represents a human life, like Marianne Ashworth. Marianne lives approximately 18 miles from Chemours. It took Chemours 3 years to begin testing her well. Many of these residents, like Marianne, learned their well tested positive when a random truck showed up unannounced with paperwork, and oftentimes pressuring residents to not take the full 60 gallons they are legally entitled to. Marianne's reality includes figuring out where to store 60 gallons of bottled water in her house, how to handle all the packaging waste, how to cook with bottled water, and how to move forward with the under-sink filter options outlined in the court order. She has no idea what sort of impact these exposures could potentially have on her children or herself, and no one can tell her. If you move further down the Cape Fear River, you end up in Wilmington, North Carolina. I live in Brunswick County and work in Wilmington. Approximately 300,000 residents in Brunswick, New Hanover, and Pender counties use the Cape Fear River as their primary source of drinking water. Chemours does not provide any bottled water and is actively fighting a lawsuit from 2 water districts who are seeking recovery costs for millions being spent by ratepayers to upgrade treatment processes capable of filtering out a problem we didn't create. While Chemours is no longer actively releasing their waste streams into the Cape Fear River, the legacy groundwater contamination from under the facility continues to seep into our drinking water supply. It is this source of legacy contamination that continues to put Wilmington and Brunswick County in the news for still having some of the highest levels of PFAS in municipal tap water in the nation. To understand what we have endured since learning of our contamination crisis, here is a graph of Brunswick's total PFAS levels since January of 2019. The average daily dose of PFAS residents have consumed in the past 3 years is approximately 114 parts per trillion. We worry this doesn't begin to capture the total amount of PFAS in our tap water because commercial labs lack the analytical standards to detect all the PFAS likely still there. A court order required Chemours to disclose the total amount of PFAS released into the river. That report documented nearly 300 different PFAS. It is reasonable to assume we were chronically exposed to these large mixtures on a daily basis for decades. We know our water districts could not filter out the PFAS, meaning what was detected in the river was likely at near equal levels in our finished tap water. One study estimates we were exposed to approximately 130,000 parts per trillion of total PFAS during the peak of our exposures. Currently, residents are left paying for their own filters or bottled water or continue drinking from a contaminated tap until municipal water districts can implement treatment upgrades. In North Carolina, like so many other contaminated communities across the globe, we are concerned about more than just drinking water. Researchers are finding levels of PFAS in river sediment, local seabirds, as well as contamination in regional alligators and fish. Wilmington's local university detected Gen X and rainwater samples on their campus, located 80 miles from Chemours. Local shellfish have not been studied in our area, but we know from other research shellfish can be contaminated with PFAS. Because our drinking water was so severely contaminated, we believe we cannot afford one more drop of PFAS from any other pathways. We know there are background levels of PFAS contamination in food packaging, indoor dust, textiles, and many consumer products we can't opt out of buying because safer alternatives are not easily available or properly labeled. Let's be clear, Wilmington and Fayetteville are not isolated incidences. We are ground zero for one chemical company's massive supply chain. I have heard scientists dismiss our contamination as too unique, and I believe this is a false narrative. DuPont Chemours may make their PFAS in North Carolina, but they sell this chemistry to a ton of manufacturers around the world who are also releasing PFAS into neighboring communities. Both Merrimack, New Hampshire, and Hoosick Falls, New York, are well-documented examples here in the United States. The constant strain and stress of watching people around you suffer is excruciating. Everyone knows someone with cancer. We have no idea what sort of body burden we are carrying from years of chronic exposures. I once had a PFAS scientist tell me they don't want to give up their waterproof jacket when they go recreational camping, and all I could remember thinking was how my friend Sandy lost her husband to liver cancer because a shoe manufacturer dumped their PFAS waste in a field that contaminated her well water. When I come to these conferences, I think about people like Abigail, a pediatric cancer survivor in Wilmington. Her doctor told her drinking lots of water is her medicine, to which she asked, is it? Is her tap water medicine if it's contaminated with PFAS? I think about my friend Tom, who is slowly drowning as his lungs fill with fluid too quickly for doctors to safely remove. He's had over 80 rounds of chemotherapy in the past 5 years due to metastatic male breast cancer. We have no idea if PFAS exposures caused his rare cancer, but he believes it certainly is not helping. I think about my neighbor Amy, who drank our contaminated water for 19 years. Last year, she was diagnosed with a rare cancer called adenoid cystic carcinoma. The cancer has spread along her facial nerves, leaving the left side of her face completely paralyzed. Amy's only goal right now is to live long enough to see her daughter graduate high school in 3 years. I think about Emma and her mom, Sarah. Sarah was diagnosed with stage 3 colon cancer a few years ago. The cancer has returned 3 times due to a gene mutation, making Sarah's body resistant to typical treatments. Emma sees how frustrating and emotionally fatiguing it is to see her mother battle cancer, beat it, only to have it return again and again. I think about my daughter's best friend, Charlotte, who has spent her childhood watching the adults around her get sick. Her mother, Kara, battled an aggressive form of breast cancer that feeds off of estrogen hormones. Her grandfather, Bob, developed bladder cancer and leukemia. A month after Bob's leukemia diagnosis, Charlotte's grandmother, Margaret, was diagnosed with a rare blood cancer. I always think about my own family. 3 years after moving to Brunswick County, my husband started losing his vision. We quickly learned he had a brain tumor. Thankfully, it was not malignant and could be removed with surgery. He is an identical twin. His brother is healthy and lives in another part of the state that does not have contaminated water. We will always wonder if the water caused my husband's tumor. I'm sharing these stories because it's important for everyone listening to see these faces and remember their names. Men and women in their 40s are getting their futures stolen from them. Teenagers are watching their parents suffer, and we can all do something about it. I am begging you to remember at the end of every test tube, microscope, and keystroke, there is a life hanging in the balance. I'm on the leadership team of the National PFAS Contamination Coalition. We represent a diverse group of contaminated communities from across the nation who collectively advocate for stronger PFAS federal regulations and push for accountability from responsible parties. We are begging you to help us. I believe in the inherent good of humankind. I believe people generally want to do good in this world. And I also believe everyone attending this conference truly wants to make the world a better place. I just think we differ on the definition of better place. I personally believe actions always speak louder than words, and the scientific community has been under attack for decades. Whether it's climate change, COVID, or chemicals, the scientific community must evolve its structure to remain relevant in the face of deep industry influences tampering with public policy making that ultimately breaks public trust. This is a slippery slope. When public trust in government institutions falters, societies begin to crumble. While the scientific community begins debating essential uses, I believe chemical companies like Chemours are already dominating the narrative and positioning their entire product lines as essential to the very policymakers who will ultimately decide what is regulated as essential or not. For example, I recently connected with a firefighter who has no sperm. He can't start a family with his wife, and he wonders if occupational exposures to PFAS caused his infertility. Our firefighting community needs your help. They don't want PFAS in their turnout gear and feel the chemical industry is controlling too many studies used for policymaking. These brave men and women are begging for more independent studies on their personal protective gear. Many don't believe their gear needs to be coated in PFAS, and they are looking for independent research studies to determine if PFAS can be deemed non-essential in their gear. Contaminated communities need easy access to affordable water and blood testing that is sensitive enough to detect both legacy and commercially relevant PFAS. We need safe and affordable technologies to break down and destroy PFAS. We need scientists to include statements of precaution in their studies instead of statements that say further studies are needed. For years, chemical industry lawyers have used this language in court to cast doubt on a phrase many scientists use for modesty. No more scientific modesty, please. We can't afford for the scientific community to pretend to be impartial or agnostic. The chemical industry is exploiting this void. Please improve scientific communications by partnering with impacted communities to release your findings. Wilmington, North Carolina residents continued to drink PFAS-contaminated water for an entire year before a journalist accidentally found a pivotal publication. Stop relying on public agencies and public leaders to do the right thing. Hold press conferences in collaboration with impacted community groups. Invest in marketing communications experts to get your research seen correctly. Additionally, partner with healthcare community to meet their clinical guidance needs. Collaborate with research institutions and cancer centers in or near PFAS-contaminated communities. We need more research that stands in the legal and policy gaps the chemical industry has intentionally created. This includes more research focused on epigenetic impacts of environmental exposures, mixture studies, and more human health epidemiological studies in global communities that have the statistical power to provide the data. We need academic and government institutions to match dollar for dollar their current investments in PFAS uses with equivalent and equal investments in efforts to replace PFAS with safer alternatives that encompass the US EPA's green chemistry principles or an equivalent. Everyone here today has a choice. We can commit to making all uses of PFAS non-essential by researching the heck out of safer, greener alternatives, because at the end of the day, what's the point in racing to outer space if everyone on Earth is too sick or infertile to enjoy it? Thank you so much for your time. It has been an honor to be here.
Thank you, Emily, for such a strong presentation, and actually a segue to our morning session. Please, if you have a question for Emily, she will be here around for the rest of the morning session, and she will be also available during our panel discussion at the end of the morning session. So, and now it gives me a great pleasure to introduce our next session toward a PFAS-free Europe, a science policy dialogue, which is hosted by Swiss Federal Institute of Technology in Zurich and co-chaired by Martin Scheringer and Zhengyong Wang. The floor is yours.
Yeah, many thanks, Itika. Can you see our slides? Yes, great. Thank you so much. Yeah, thanks again. Welcome to our session. Maybe just first introduce ourselves. My name's Zhengyong Wang. I'm a senior researcher at ETH Zurich. As an environment chemist by training, I have studied the life cycle, releases, and environmental fate and transport of PFAS since the last, about 15 years. Very happy to be here to chair this session. So give floor to my co-chair.
Yeah, hello, also from my side. My name is Martin Scheringer, and I also work in Switzerland at ETH Zurich, like Jean-Min. And I share my time also between ETH and Resitox at the Maastricht University in the Czech Republic. And my background is also chemistry, and my research interests in the area of PFAS is properties, uses, and emissions of PFAS, and also the resulting human and environmental exposure. And in addition, I think it's very important for chemicals management to have an effective science policy interface. And that is one of the main topics of the session today, to think about what kind of science policy interface do we need in the area of PFAS to have an effective and successful management of the PFAS problem in the future. Thank you.
Yeah, thanks, Martin. So before we go into the session, we also like to share some, we have made a poll in the WUFA platform, and we have received. So it seems that we have already received quite some results. So far, from the poll results, we have many academic scientists joining us, 66 were on the platform. Also many scientists from the government institutions, about 30 of them, from 9 from business, and 6 from the civil society organizations. Most of people are very already experienced in the PFAS field, while we also have about 20 participants of rather new to the field. Welcome. And most of the participants are from the North America, and there are about like 40 from Europe, about 10 from Asia Pacific, Latin America, and African regions. Also, many welcome to our session. Before going to the session, I will also just like to take the opportunity to make you aware of there's a new reports published by OECD very recently. In the reports, there's a recommended revised PFAS definition. It reads, PFAS are defined as fluorinated substances that contain at least one fully fluorinated MEA2 or methylene carbon atom without any hydrogen, chlorine, bromine, iodine atom attached to it. The rationale is to have a general PFAS definition that is coherent and consistent from the chemical structure point of view, and is easily implementable by non-experts. I've also put a link here, or you can find it on the OECD PFAS web portal. I would really encourage you to read these reports and adopt the recommendations in this report in terms of using the PFAS terminology, so that we are always everyone is on the same page when communicating about PFAS. Here, just also some very quick examples about the new revised PFAS definition entails. On the left side, the blue with the white background. Those are the examples of PFAS that already meet the definition by the previous definition. And on the right side, you can see the examples of PFAS that are added under the new OECD definition. It's mainly like including the PFAS with functional groups on both ends, and also PFAS that has only a cyclic ring without perfluorocarbon chain on the sides, and also PFAS like with aromatic ring somewhere in the functional groups. So with this, there's also would like to show you that there are also many compounds that they are not PFAS, but it doesn't mean that they are not important, but they're just not within the context of PFAS, such as like the fluorinated aromatics on the most left. You can also find these figures in the reports to give you more detailed information. So PFAS is a very wide class of chemicals. However, they do share many similar properties, such as the high persistence and the ability to accumulate in the environment and biota. And also many, like the existing studies of many PFAS already shown that they do have other hazardous properties, such as toxicity, bioaccumulation potential, and all like greenhouse potential. So there have been a lot of call recently about really managing the PFAS as a class, as you may have heard from the last week tonight, yesterday. And I just want to highlight that it is something that we really need to think about to like taking into account the high persistence of PFAS and to manage them as a class. I would like to give the floor to my co-chair.
Yeah, thank you, Jarmin. And in addition to the background on chemicals that you have heard now from Jarmin, I would like to address the background of our session today regarding the policy developments. And just a few words about this. Here is first the global level. There is the Stockholm Convention on Persistent Organic Pollutants. And as it says here in blue, the chemicals that have been addressed or are being addressed right now are mostly so-called long-chain PFAS or carboxylic and sulfonic acids. Chemicals that have been listed under the convention are mostly PFOS and related compounds and P4 and related compounds. And importantly, this process is always continuing or going on, and currently being evaluated for listing under the convention is the hexane sulfonic acid and related compounds, and also the long-chain carboxylic acids and related compounds. Then a bit more specifically, in terms of geographic focus, we want to look at the EU, the European Union, and here again you see two colors. Black is showing chemicals that have been already mentioned or have been handled or are handled under the Stockholm Convention. But in blue, we have interesting, important additions. One important mechanism in the EU to regulate a chemical is the so-called restriction. And under the already restricted is, for example, here the important additional group of 6,2-fluorotelomere-silanes in spray products, in addition to the ones 2,2-P4 and the long-chain PFCAs. And importantly, also this process has not been finished, of course, but it is an ongoing process, and there can be new restriction proposals. And interestingly, now there is first the hexanoic acid and related compounds that are being evaluated for restriction, and importantly, and we'll hear more about this, the entire class of PFAS. There is a proposal for restricting the entire class of PFAS in the EU. Then, in addition, the EU has also what's called SVHCs. This is substances of very high concern. And these substances are flagged for additional measures and regulation or options for regulation. And here there is HFPODA, or marketed as Genex, that is a substance of very high concern, and also the butane sulfonic acid, the C4 sulfonic acid, that's also listed as a substance of very high concern. Given all this, we may ask ourselves, is this all we have to do? Are we good? And probably we are not. We have heard already that there are more and wider and bigger concerns. So what is it that needs to be done in addition to all these important ongoing efforts? And that's the goal of the session today. We would like to offer a platform for regulators and scientists to talk about the big picture of PFAS science and PFAS policy developments, and how scientists can effectively support the policy developments that lead to a PFAS-free Europe. That's the focus of our session, but of course this also goes beyond Europe, and many of the thoughts may also apply to other parts of the world. And specifically, we would like to analyze and identify when there are policy windows where scientific input is needed to be effective in a policy process. And related to this, also the question of what are the research questions that should be targeted, that are important, and also what is their order, the right order, what are the best priorities for these research questions. To talk about these important aspects, we have 4 contributions, and then after a break, also a panel discussion at the end of the session. The contributions are first by Valentina Bertato from the European Commission, and she will speak about the important new scheme, let's call it the EU Chemical Strategy for Sustainability, and PFAS in the context of that important new regulatory scheme. Then the second presentation will be by Lena Vierke and Jonas Schulze from the German Environment Agency, and they will speak specifically about the PFAS restriction proposal that I mentioned already as a very important piece of policy development. Then in the second part, there is Anna Kerman from Örebro University in Sweden, and Anna will speak about analytical approaches of PFAS, but not just technically, but in the context of policy action and regulation. So what is really needed? What kind of analytical approaches do we have to actually implement and enforce regulation? And the last speaker is Ian Cousins from Stockholm University in Sweden, and Ian will talk about the question of are fluoropolymers really polymers of low concern? Then we have the break, and then we have the panel discussion. And I think that's what we have to share at the beginning of the session. Thank you very much for your attention.
Yeah, thank you, Martin. The next I would like to welcome our first speakers. The talk from Valentina Bertato. Yeah, she works at the European Commission at the DG Environment. So she's going to share with us about the European Chemical Strategy for Sustainability and the PFAS.
So thank you for inviting me to this conference to present the European Strategy for PFAS. This presentation will be mainly in two parts. I will present first of all the policy background, why we have a European strategy for PFAS, and then I will give a bit more details on the chemicals legislation and also on some other legislations where we are addressing the concern of PFAS. So starting from the policy background. We have the conclusions from the Council of the European Union that were asking the Commission to develop an action plan to eliminate all non-essential uses of PFAS. This was indeed the first and important political message we got to start working on this group of chemicals. This happened in June 2019, and on the same year we had another discussion in the European Council concerning PFAS, where a member state, the Netherlands, announced that they wanted to prepare a REACH restriction on the whole PFAS group, so to ban the use of these substances via the chemical legislation REACH. And this was supported by 8 other member states. Again, when the new Commission started to work a few years back, a group of member states wrote to the new commissioners to ask for a PFAS action plan. So they specifically asked us to look at PFAS as a group, no longer as substance by substance, and to use all the available regulatory and non-regulatory instruments that we have in the European legislative framework. This was followed by the European Parliament in the resolution on the chemical strategy that in the meanwhile the Commission was developing. They asked for an action plan on PFAS, again repeating the comment also of the Council, to have a speedy phase out of all their non-essential uses. And they also specified that they wanted us to work on the development of safe and non-persistent alternatives for all the uses. So what did the Commission do? We had the European Green Deal, and in the European Green Deal, we have a specific action, a zero pollution ambition for a toxic-free environment. And it is within this action that we also have the commitment to develop the chemical strategy for sustainability and to look specifically at very persistent chemicals, such as PFAS. So this is what we did. We drafted and discussed it internally in the Commission, the chemical strategy for sustainability. And there we have very clear references to the actions that we need to do on PFAS. We say that they require special attention because of the many cases of contamination that we have seen in Europe, but also outside Europe. And that we needed to propose a set of actions to address the use and contamination with PFAS. Here we follow the recommendation of the Council and the European Parliament, and we committed to the phase out of the use of PFAS in the EU, except when these uses are proven to be essential for society. And indeed, to prove this, that they are essential for society, is going to be a key discussion point for us in the future. Specifically, the Commission decided to start already working on a specific use of PFAS, the use in firefighting foams, because we had already done some work with the European Chemicals Agency on this use, and also because this use was responsible for many cases of contamination. And I have provided here the link to this intention, to the preparation of this restriction dossier. What is also asking the chemical strategy for sustainability for PFAS? The Commission is committing to define criteria for essential uses. That will be useful for the case of PFAS, but it will apply in general to all the most harmful chemicals and also outside of the chemical legislation. And then we are looking more generically at some of the concerns that is also shown by PFAS, and to try to introduce specific classes and criteria in the regulation on classification and labeling, so to take into account persistency and mobility. And this is indeed very important for the hazard assessment of PFAS. And then the Commission also committed to introduce new categories of substances of very high concern under REACH. And again, here the reference to very persistent and very mobile substances, so that PFAS could be identified more easily in the future as substances of very high concern. So in addition to the communication for the chemical strategy, we also have a specific technical document on PFAS, what we call the PFAS staff working document. And here we look at all the actions that we can do to address the concern of PFAS. So not only the chemical legislation, on which I will focus in this presentation, but also all the other regulatory tools we have in the EU. So from food contamination to the legislation concerning water, the industrial emissions, waste, soil. We will work at international level, and we have also foreseen specific funding under the Research and Development Program under European Union to address the remediation of PFAS contamination, but also the development of alternatives. So today I will not talk about all these fields because it would be too long, but as I said, I will focus on the chemical legislation, and then I will say also something more on the water legislation and on the food contaminants legislation. But at the end of this presentation, I have also included additional slides with more details on these regulations that you can consult later on if you are interested. So let's start with the chemical legislation. So the chemical legislation in the EU is REACH regulation. And we had already started to work on PFAS under REACH even before the PFAS strategy. We have basically restricted all long-chain PFAS, PFOS, PFOA, C9, C14, PFCAs, and PFHXS is still ongoing, the process, because it is under the Stockholm Convention, the international restriction. Then we already identified as substances of very high concern some of the alternatives to the long-chain PFAS, so two short-chain PFAS, GenX and PFBS. And their concern was identified especially because of persistency, mobility, the potential for the long-range transport, and the adverse effects that we can see, considering that these effects are in most cases irreversible. Another short-chain PFAS, PFHXA, is currently in the restriction process with a dossier that was prepared by Germany. And then, as I already mentioned, we requested ECHA to prepare a restriction dossier on all PFAS in firefighting foams. And here you have the links to the specific information on these two processes. So what about the other uses of PFAS? You might have noticed that we have decided to move from a substance-by-substance approach to a group approach. The firefighting foams restriction will be on all PFAS, not on specific ones. And we have a group of authorities, 4 member states, the Netherlands, Germany, Denmark, and Sweden, plus Norway, that are working on a restriction dossier on all PFAS in all the other uses, excluded firefighting foams, so that at the end we will have a full REACH restriction on all uses of PFAS. So I will not go into the detail of this because I know that there is a colleague today presenting specifically this activity, but I have added here the links where you can find all the information. So this is it for the chemicals legislation. As I said, I'm going now to go briefly through other European legislations where we are trying to address the concern of PFAS. Because in the chemical legislation, we will indeed address it at the source. So trying to restrict the uses where they are not essential and reduce the emissions. But in the meanwhile, we also need end-of-pipes solutions. So we need to control the environmental compartments where there have been emissions and where there is contamination. And unfortunately, one of these compartments is the drinking water. We had a very serious case of drinking water contamination in Europe, in Italy. And this is why some member states have already started to set limits in drinking water. And with the new drinking water directive, the Commission recently set European limits. So we have a limit on a sum of specific PFAS, that is 0.1 microgram per liter. and the limit also on all PFAS, 0.5 microgram per liter. And this is the first time that we have in the European legislation a limit for the whole class of PFAS. This will become applicable by January 2026, but in the meanwhile, by January 2024, the Commission needs to publish technical guidelines on analytical methods, because we currently don't have a standardized analytical method to measure all PFAS, but a lot of work is ongoing on this field. Then we have been working under the food contaminants regulation to regulate the level of PFAS that can be found in food, because unfortunately, if the soil contaminated, if the water is contaminated, we can have also contamination of the food. So here the Commission is working based on an opinion from the European Food Safety Agency that you can find here in this link, that is setting a very low tolerable weekly intake for 4 PFAS. This is 4.4 nanogram per kilogram of body weight. This is much lower than previous limits that were set by the agency for PFOA. And the conclusion of the agency is that the part of the EU population exceeds already this CWI, so there is a potential risk due to the exposure to PFAS in food. And we have already started the discussion with the member states on the basis of this opinion to set the maximum levels of PFAS in specific foods. So what is happening also under several pieces of legislation concerning water is that they are undergoing what we call an evaluation for a potential review. So here you see a lot of acronyms, but I try to explain them in the slide. So we have the Urban Wastewater Treatment Directive that is being revised, and we will consider contaminants of emerging concern there, including PFAS. We'd also have the Sewage Sludge Directive that is under evaluation for a review. And this is important because PFAS that go in this water treatment plants, they often end in sewage sludge. So we need to control the contamination there. We will try to set limits under this directive. And then we have the group of directives that concern surface water and groundwater, so the Environmental Quality Standard Directive, the Groundwater Directive, and the Water Framework Directive. Also here we have an evaluation ongoing with an impact assessment and the setting of limits for PFAS. Still to be defined, there will be specific limits for PFAS that are often found in the water, or if it will be a family, a group limit, as the one we have in the Drinking Water Directive. So here I'm speaking to an audience of scientists mostly, and I was also thinking on what you could do to help us to progress with our actions in the EU for PFAS, for the PFAS strategy. And the first thing I thought is that you have indeed already helped us a lot. Because we are at this point, we have a EU PFAS strategy and actions under almost all the pieces of European legislation for the environment, because you raised the issue. You published a lot of papers. We had the Madrid and Helsinki statements that were really a push for action. But we also need you to continue with this work because we will need more data, more work from scientists to progress with the action and also to justify them in some cases. As I already mentioned, we will need analytical techniques for all the PFAS, the whole family, because we are going to act now on the whole group, not anymore on specific substances. We will need monitoring data in the environment, including in remote locations, if we want to continue preparing a dossier for inclusion also of PFAS under the Stockholm Convention for an international ban. And we also will need biomonitoring data, presence of PFAS in organisms. Then another very important point is information on uses and emission, especially on new PFAS, because the information provided by industries in some cases very limited. An important point, as you have heard, is the discussion on essential uses. We want to restrict all PFAS except in essential uses, and also here ideas from scientists will come. There were already papers published even recently, so please continue to do so, to reflect on this, to help us. And then, as I said, we have funding for research and development in the EU. So when there are calls concerning PFAS, as it already happened and it will happen also in the future, please present proposals so that we can also advance on the side of research. So that was my last slide. Thank you very much for listening. And I'm here now to address any question you might have.
Great. Yeah, many thanks for the presentations. I think this is really interesting to hear that there are so many different activities undertaken within the EU, and there are also so many activities that the scientists or the scientific community can really support. I think also we have the Valentina with us in live, right?
Yes, indeed, I'm here. Hello.
Yeah, hi. Yeah, thank you. And yeah, we do have some questions for you.
So,
Yeah, so maybe yeah, maybe we can start with a little bit there's these questions asked by Rainer, like uh, yeah, maybe we can start with a bit more like the 4.4 nanogram per kilogram body weight weekly uptake is for the sum of which 4 PFAS is proposed or enacted.
Yeah, this is a proposal from the European Food Safety Agency in an opinion, and it concerns for PFAS, PFOA, PFHXS, PFOS, and if I remember well, PFNA. If the proposal it's enacted, how it works in the European legislation, for example, the food contaminants legislation, we have the opinion of the agency, in this case EFSA, and then the Commission prepares a proposal for setting limits, in this case in food, and then this is discussed with the member states. So the current status is that the discussion with the member states have started, but they have not been concluded yet. So we will need to wait for a few more months before seeing the limits on PFAS in food.
Yeah.
Should I try to address the other questions as well? Because I see many are on the definition, but those I think are better to be answered by the colleagues who are working on the restriction that will speak later.
Yeah. Yes. Maybe also just one question is with regarding to there's also a follow-up question by Miriam. Like, will EFSA be moving towards a TWI that considers PFAS as a class? I presume the TWI definition and also for drinking water will be functionally defined according to analytical methods.
Yeah, I mean, the TWI that is set by EFSA, and I must say I'm not an expert on the food regulation because I'm working for REACH, so the chemicals legislation, but it was set taking into account the PFAS that are currently more often found in food. So this is why they are focusing on these 4 PFAS. Of course, things evolve, so this could be reviewed, as it was already reviewed 3 times, if I'm correct. And the TWI is based not really on analytical methods. It is based on the toxicological endpoints. So they looked at all the available studies, and in this case, they took as a most sensitive endpoint the effects on the immune system. And this is a new approach for PFAS, and this is why we have such a low limit. Then after, when the Commission prepares the proposal and member states discuss, they take into account also if the limit can be implemented, so the analytical methods, but these come after. But please again consider that I'm not really an expert on the food regulation, so yeah, this is just from my knowledge.
Yeah, many thanks. there's also maybe one more very technical questions, like what type of methods are you hoping to see that can measure all PFAS? What total fluorine methods quantify?
Yeah, I think that also in this case there will be a specific talk on methods, but if I can speak about what we would like to see maybe that could help us for the implementation of the restrictions in the future, total fluorine methods, indeed, they are the way forward. I mean, we need to be able to analyze samples for the whole family of PFAS to have an idea if PFAS are present or not. And in many cases, I think they would be sufficient to understand if a certain sample complies with the restriction. In some other cases, maybe it would be needed to know which PFAS are present, and then we would maybe need, together with the total fluorine, also that could be used as screening methods, also more specific methods, so to quantify specific PFAS. But this is just the idea I have now. We will need to confirm this when we move forward with the restriction, but also with the other EU legislation to really understand the analytical needs we will have.
Thank you very much. Your microphone is muted, so I think that the reason is that we have the question here from the audience, so please.
Great. Very nice presentation. Just a question regarding if you have any idea already on some essential uses you might consider essential. I'm curious what they might be.
Thank you for the question.
Yeah, it is very early to address this question because the uses are going to be analyzed in depth in the 2 restriction dossiers that are ongoing, and in parallel we are having a policy discussion internally in the Commission on criteria for essential uses. So we will hope that in the next months something more will be known, but we are indeed in the early stages of this discussion. And it is interesting because we are having the 2 discussions on the generic criteria and a specific case of PFAS in parallel. So let's hope that this will help to progress.
Yeah.
Thank you very much. I think that this will be also part of the panel discussion at the very end. So thank you, and we can move to the next presenter.
Yeah, many thanks, Itka.
Thank you again for all the interesting information from that presentation. And now we move on to the next speaker, who is Anna Kerman. Anna is an associate professor of environmental chemistry at Örebro University in Sweden. And she will perhaps directly take or continue with some of the important points mentioned now by Lena and Jona, namely analytical methods and what they can do, and if they can deliver what the policy developers and regulators need. So Anna, are you ready?
My name is Anna Kerman. I'm associate professor in chemistry at Örebro University in Sweden, and I'm going to talk about analytical approaches of PFAS in support of policy actions and regulations. So during this talk, I was hoping to introduce a little bit about PFAS and more specific PFAS monitoring, and touch upon some of the analytical challenges, but also possibilities that we currently have. I'm also going to present the current analytical approaches available in support of policy actions and regulations, and finally end with a little bit of an outlook and some questions for discussion. So in the context of PFAS monitoring to support policy and regulations, I think it's quite important to understand that the compounds we are measuring containing fluorine can originate from different sources. So the most common form of fluorine in nature is actually the inorganic fluoride salts. There are a few examples of natural or occurring organofluorine, for example, this fluoroacetate molecule in the middle here that is produced by certain plants as a protection for grazing. So what we are interested in here is, of course, the anthropogenic organofluorine. So it's the man-made organofluorine compounds. And as everyone is fully aware of, this class of per and polyfluoroalkyl substances is a quite big class. So current definition includes all substances containing at least one perfluorocarbon moiety. So this brings us many different substances. From an analytical point of view, these substances can be divided into three main groups, also as suggested by Wang et al. So first we have the perfluoroalkyl acids, which are extremely persistent and strong acids that contain a fully fluorinated backbone. Second, we have precursor compounds, and here we have many different examples of compound classes. For example, we have precursors that can transform into the sulfonic acids, and we have precursors that can transform into the carboxylic acids. So these are the precursors to our very persistent perfluoroalkyl acids. And this is just two examples of precursor groups. So there are many, many more. Finally, the last group here on this slide is the polymers, the fluoropolymers and the polyfluoroethers that has a fluorinated backbone. So when we come to monitoring these compounds, we do monitoring for regulatory purposes. Looking at the situation in the EU today, we have a tolerable weekly intake defined by EFSA for 4 of these perfluoroalkyl acids. So it's PFHXS, PFOA, PFOS, and PFNA, and they all belong to what is called the long chain acids. If we also look at the new EU Drinking Water Directive, the updated Drinking Water Directive, there is a number of other PFAS substances included in the sum of 20 PFAS. And now we also have some that is classified as short chain acids and even more of the long chain acids. So they have all different properties that I will not go into detail. So this is the regulatory context, you might say. But the contamination profile and the usage of PFAS looks a little bit different. So if we want to study how the contamination actually looks like, we will also find some acids that is called ultra short chain acids that contains only 1 to 3 perfluorinated carbons. And then, of course, we have this huge group of precursors and also transformation intermediates of precursors that are being transformed into the perfluoroalkyl acids. And here we find a number of different known substances that have been used in firefighting foam, for example, and many, many different, and even some unknown precursors that we currently haven't identified yet. So what is determining what we are looking for? So what are being monitored and why? So one obvious reason to monitor PFAS is to comply to different regulations, also to study health effects and impacts of PFASs, study how they behave and the removal efficiency, for example, producing drinking water or cleaning sewage, or even remediate contaminated areas. and then we also do a lot of research studies to look at the environmental distribution of fate and also occurrence of PFAS in products, environment, and humans, including trying to find out some identities of yet to be identified PFASs. So what we have in this picture is a quite different situation where the more research-based studies include a large number of PFAS. We have a lot of screening studies, and when we are moving up to comply to regulations, we tend to have a much lower number of PFASs in our monitoring, and also fewer different matrices. We do put some different demands on these studies. So the screening studies, the more explorative studies, or even you can call it warning signal systems, they tend to have a lower demand for standardized methods, a lower demand for be able to show high specificity for certain substances and even high accuracy, while moving up to the methods needed to comply to regulations that can also be used for risk assessment. There we have a much higher requirement for standardized methods. We have a very high requirement for specificity and an accurate quantification. So some of the challenges for the analytical chemists then, and also for policymakers, is that the high standardization required might prevent the development to generate the data needed to move forward in hazard assessment of the whole group of PFAS or a larger group of PFAS. So we do have a situation today where we know that there are overlooked compounds that hasn't been studied so much. They include precursor compounds, different intermediates and transformation products, very mobile PFAS, and also more volatile PFAS compounds. Another challenge that we are facing is a demand for low quantification levels. So the European Food Safety Agency has now reduced the tolerable weekly intake with 3 orders of magnitude from only year 2008 to last year, which definitely puts a great demand on the analytical methods used. Another example is the Miljöstyrelsen in Denmark that recently reduced the limit value for the sum of 4 PFASs in drinking water to a very low limit value of 0.002 microgram per liter. We also need to take into account the precautionary principle. So the precautionary principle enables us to adopt certain measures when we have scientific evidence, but it's a bit uncertain. So there is some evidence that there might be environmental and human health hazard, but it's a little bit uncertain. And if it's deemed that the consequences can be very high, we should go and apply to the precautionary principle. And this could also be in the context of the new addition to the revised drinking water directive in Europe, which include a group approach for PFAS total, meaning the totality of per and polyfluoroalkyl substances with the threshold concentrations of 0.5 microgram per liter. So taking these measures means that the whole group of PFAS is deemed to be of human health hazard. And even though we don't really know exactly which PFAS compounds we have in this PFAS total group, the stakes are high enough to motivate to use this group-based limit value. But the question is then, how can the analytical methods comply to this? In order to get an overview of the analytical possibilities, I've chosen to use this fluorine tree, dividing fluorine into different parts, starting with total fluorine. So if we measure total fluorine, it can be either inorganic fluorine or organic fluorine. If we are able to remove the inorganic fluorine, the organic fluorine itself can be extractable or adsorbable, depending on the method, but it also can be non-extractable. And from the part of the organofluorine that we are able to extract out from a sample, we do find the target organofluorines if we use the target PFAS method, for example, but we also might have unidentified or unknown organofluorine. And if we start up here, we have a very low specificity. So here we can't say for sure if it's a PFAS compound or not. If we go down here, we have a very high specificity that we know with a very high degree of certainty that we are looking at PFAS compounds. So I would like to just go through a little bit the different possibilities available today. So obviously, starting with the target PFAS, we have a very high specificity and also very good sensitive methods for 40 PFAS or more. But the question is it possible to target all the PFAS using this kind of methodology? Do we have commercial standards enough to include more and more PFAS? So there's definitely a number of challenges using this method. To overcome some of these challenges, it's getting more and more useful to look at a suspect list or even to do non-target screening to detect known unknowns or even to us unknown PFAS. So this is a great instrumentation. However, there's some limitations regarding to be able to quantitative give values for PFAS, and also there is some challenges in the data handling and the process to identify signals as PFAS. Another method currently available is the total oxidizable precursor assay, the TOP assay, in which a precursor compounds with a number of perfluorinated carbons is oxidized using hydroxyl radicals, creating a number of oxidation products that can be measured with ordinary target PFAS analysis. So the good thing here is that we can use existing instrumentation, which is very sensitive, but some limitations include that we do know that not all PFAS structure will undergo this hydroxyl radical oxidation, and also some matrices are quite challenging to use with this oxidation reaction. However, there are method developments going on to use other more complex matrices compared to soil and water that was originally published by Hutz and Sedlak from UC Berkeley. Then I would like to move into the total assessment of PFAS, and I have chosen to divide it into 3 different parts. So one is PFAS total, which is a very, very challenging methodology to use, which I will come back to in a second. The second is assessing PFAS total by try to extract or adsorb all the organofluorine in a sample. So here we use extraction methods that are suitable for the sample matrix in question, and then we use some sort of fluorine specific detection. And the third part is total fluorine, which is actually just a direct measurement of fluorine using a fluorine specific detection. And here we don't have a problem of maybe losing some information during extraction or cleanup. So going back to PFAS total, which I said in the previous slide was very challenging. So there are a few technologies that are specific for perfluorinated substances, and that is what we are trying to achieve. We want to target the substances that have this CF2 moiety in its structure. So the methods that can do that currently published is the X-ray photoelectron spectroscopy and the fluorine-specific nuclear magnetic resonance spectroscopy. So both these methods can specific detect these CF2 groups. However, there's some limitations in the detection limit that makes them useful for certain applications only at the moment. There are a number of techniques or instruments available that are specific for fluorine. That include combustion ion chromatography, the particle-induced gamma ray emission spectroscopy, the inductively coupled plasma mass spectrometry, and the continuum source graphite furnace molecular absorption spectroscopy. So all of these methods have been published, and they are specific for fluorine. So altogether, we have a number of existing methods that can be used in support for policy and regulation, depending on whether we want to target specific PFAS, if we want to try to target the sum of acids and their precursors, or if we want to try to do some sort of PFAS total assessment. All of them have different limitations, benefits, and drawbacks that I try to summarize here, but I will not go through it in detail. And the final column here is showing examples of standardized methods using these different approaches. And as you can see, this column is quite empty, indicating that we are lacking this standardization step for these analytical methods. There's also some implications for the PFAS total assessment that I would like to briefly also go into, because I think it's important to mention. So whether you aim for a fluorine-specific detection, there's always this drawback that we have in some matrices quite a lot of inorganic fluoride that we do need to remove somehow. We also have the question that there might be other organofluorines that we are not actually want to target, which could be some of the more low fluorinated structures used for pesticides applications or in pharmaceutical. And finally, when we are using different extraction methods, we will introduce some sort of selection. So if we're trying to extract out organofluorine and be selective towards what we want to target, we also risk of losing important information and perhaps even important PFAS substances that are not extracted out. So these are some of the implications currently when talking about PFAS total assessments. So finally, I would like to end with some outlook and discussion points regarding analysis in support of policy actions and regulations. So first of all, I think we can all agree that we are currently needing analytical approaches to find these signals to preferably early protect humans and environment. And we all can agree that these signals need to be very cost efficient and also to be inclusive, so that we are not just looking under the light post, but we are also being able to detect new and maybe unexpected threats. So talking something about a baseline value which is classified as normal, and if there is a signal saying that something is happening, we will be able to detect this signal. One single analytical approach will probably not fulfill all the policy goals. So talking about PFAS total, for example, there's currently no single method that can fulfill the requirements needed, and there probably need to be some sort of selection or prioritization for the requirements for a PFAS total assessment, or several methods has to be used. There's also this gap between research methods and regulatory used method, and this gap consists basically of the level of standardization, which in turn depends on how the methods have been validated and tested. And this is something that I think in future it's very important to discuss. So for example, can we accept pre-validated methods for regulatory use in order to overcome this sometimes very big hump of requirements needed in order to standardize a method, and basically use research methods that has been pre-validated. And also, how important is it that we actually know what we are measuring in order to for sure set a threshold limit, versus how important is it for us to actually include all possible substances in a group, for examples. So when we're talking about PFAS or PFAS total, we might want to rely on a signal that could possibly include some compounds that we didn't intend to include from the beginning, but that might be a requirement in order to get the total assessment, so to speak. So that was a few questions from my side, and I will be happy to discuss them further with you. I also had one more question that I forgot, and that is if regulations can make use of signals rather than concentrations of specified substances. So a signal could be a deviation of some sort, a deviation from normal, and can this be used rather to have a set guideline value of a numeric number? So that's something also that I think would be quite interesting to discuss. I will be happy to be included in such a discussion, and my final slide is just a list of references that I used or mentioned in my talk. So thank you very much for listening.
Thank you. And Anna, are you online?
Yes, I am.
Oh, good to see you live. And Jitka, do you want to show the questions again? Yeah.
Yes, we can start from the questions. We have few questions in the WUA, and we can also take questions here. I really like the question in WUA, which were asked by Melissa, I believe. Are industry analytical chemists in any way being helpful to identify unknowns?
So if industry analytical, sorry, I saw the question for a minute here, but are industry analytical chemists being helpful to identify unknowns? Well, that's a quite broad question, but I guess my answer would be I think the industry analytical chemists, they can be extremely helpful because I think they have perhaps a different perspective and different base of knowledge than the chemists working out on that are working in the universities or research institutes. But it was quite a broad question, so I'm not entirely sure I answered it correctly, but I would say yes to that question.
At the very end, at the panel, do we have any question here from the audience? It seems that we don't.
If I may, Jitka.
So if you have any question, ask now, or we can move to, we have 2 minutes, so we can ask some of the questions.
If I may intervene or interfere, I found one question interesting. That was what's driving down the LOQs? Is it hazards of particular chemicals, or what else is it that's driving down LOQs to lower values?
So what is making analytical chemists to strive for lower and lower LOQs? I would say definitely it's the requirements put from risk assessments, and I think also that is somehow needed. So I think as an analytical chemist, you are quite satisfied with your method when you have a certain margin towards the guideline value or the yes or no limit. And there's really no need to go further. But if those limits are being lowered and lowered, the analytical chemist will respond and definitely make sure that the methods can comply in a safe and secure way.
Thank you. Very good. That was all from my side. I think now we may be at the point that we move on.
I don't think that we have any questions from the audience, so we can move on.
Very good. Then the next speaker is Ian Cousins, and we'll also again hear or see the video, I guess, and then talk to Ian live.
Hello and welcome to my pre-recorded presentation. My name is Ian Cousins and I'm a professor at Stockholm University in Sweden. I'm an environmental chemist by training and I've been conducting research on PFAS for over 20 years. Today I'd like to discuss whether fluoropolymers are really polymers of low concern. The talk largely discusses the conclusions of two papers. The first paper was published in 2018 and authored by scientists from the manufacturing industry, plus a couple of academics. This paper claims that fluoropolymers are polymers of low concern. And the second paper, published last year, was led by Rainer Lohmann and co-authored by me. In this paper, we challenged the conclusions of the first paper. So what are fluoropolymers? Well, first of all, fluoropolymers belong to the class of substances known as PFAS. We can divide PFAS into non-polymers and polymers as shown in this figure. And among the fluorinated polymers that are PFAS, we have the fluoropolymers, but also polymeric perfluoropolyethers and side chain fluorinated polymers. Fluoropolymers are a distinct subset of fluorinated polymers based on a carbon-only polymer backbone, with fluorine atoms directly attached to this backbone. Fluoropolymers are dominated by polytetrafluoroethylene, or PTFE, PVDF, or polyvinylidene fluoride, and FEP, fluorinated ethylene propylene, are the second and third most produced fluoropolymers, and then there are many others. And although there has been pressure on PFAS, the manufacture and use of fluoropolymers has increased in recent years, and the fluorochemical industry expect and hope that this trend continues. Juliana Gluger, a postdoctoral researcher in Martin Scheringer's research group, recently reviewed the uses of PFAS. She identified more than 200 uses for more than 1,400 individual substances. This figure shows some of the most used PFAS that she identified. Some of the best known uses were not the most used in terms of volume. And fluoropolymers tended to dominate the use volumes, as shown by the dominance of the light blue bars on this graph. A few definitions are useful before continuing. First, fluoropolymer substances are materials of known chemical structure, for example PTFE. However, the products sold by various manufacturers are not just pure PTFE of the same grade. The particle sizes are different, and PTFE can, for example, be purchased in either granular form or fine powder form. These different grades have distinct uses. They are also not 100% pure and will contain impurities such as oligomers and residuals of chemicals used in the manufacturing process. These fluoropolymers are purchased by product manufacturers and incorporated into finished articles using various processes. Finished articles could be PTFE tape, a waterproof jacket with a PTFE membrane, or PTFE cookware. There are different processes for making fluoropolymer products. Some do not require PFAS-based processing aids, for example, granular PTFE, and these days fine powder PVDF do not require PFAS-based processing aids. PTFE fine powder, however, has been made by emulsion polymerization using salts of PFOA as processing aids historically. And now fine powder PTFE is made with a range of alternative low molecular weight PFAS, which I'll discuss more on the slides that are coming. So are fluoropolymers problematic in the use phase? Here I'll draw on the arguments from this paper I mentioned at the beginning that was authored by the chemical industry. And I'll use the example of PTFE in non-stick cookware. The argument is that PTFE is an inert, non-degradable substance that is also non-bioavailable. It is considered too large to cross cell membranes. Also, it is argued that modern PTFE contains very low residual impurities. And it's true that a large amount of these impurities are these days removed during manufacturing. Now, it's known that PFCAs can be produced in the air above the pan by pyrolysis if the pan is heated above 250 degrees centigrade, which is above the typical cooking temperature, but this temperature can occur if you leave your pan on the stove. But the levels of the long-chain PFCAs produced by pyrolysis tend to be very low, so this is considered to be a low risk. So do we buy these arguments that PTFE is a polymer of low concern based on the fact that exposures during the use phase are low? The answer is no, of course, because this totally ignores the life cycle of fluoropolymers. If we focus only on the use phase of the life cycle, we ignore the biggest impacts which occur during the manufacturing and end-of-life parts of the life cycle of fluoropolymers. It is well known that historically, fine powder PTFE was made with salts of PFOA. PFOA is still used for making PTFE in China, where it is released to the air and water in large quantities. And countries outside of China are making PTFE with fluorinated alternatives, which are also PFAS. A couple of the best known alternatives are included here, that is HFPODA, also known as Genex, and Adona. These alternatives are perfluoroalkyl ether carboxylic acids, so their ether linkages are inserted into the perfluoroalkyl chains. The historical release of PFCs was huge from the manufacturing of PTFE. This paper from 2006, which was co-authored by me, shows that 80% of the PFCAs ever emitted originated from fluoropolymer manufacturing. Now, this is not disputed by industry. This was co-authored by industry. And we also know that many of the problems associated with PFAS are a result of the PTFE manufacturing. The movie Dark Waters, for example, was all about the high exposure of people living near the Chemours fluoropolymer manufacturing plant in West Virginia. And the alternatives such as Genex are continuing to be in the news today. When PFOA was phased out, each company came up with their own alternative. Here are a few. It took a while to figure out, but we realized that the alternatives were very persistent and very mobile in the environment and would thus contaminate drinking water. They do appear to be less bioaccumulative than their predecessors, but high persistence and mobility are more and more being recognized as highly problematic properties in themselves. On this slide are some of the reported problems of some of the alternatives. We're also discovering that it's not just these processing aids that are being released during manufacture. Volatile fluorinated byproducts contribute to global warming. There are also multiple low molecular weight PFAS being discovered around these plants, and we know little about these substances. For example, Chemours themselves listed 250 novel PFAS at the Fayetteville plant in North Carolina, and the US EPA identified multiple PFAS in soils in a paper published recently in Science. What about end of life? Can fluoropolymer waste be handled safely? Like most plastics, only a small percentage of fluoropolymers are recycled, and this recycling has not been industrialized. Small particles of PTFE are known to enter the environment like other microplastics and have been found in Mediterranean fish and in Arctic sediments. Can fluoropolymers be destroyed during incineration? There are a few studies, mostly by industry, and it's known that it requires at least 800 degrees and maybe as much as 1100 degrees centigrade for several seconds to destroy PFAS. It's uncertain if any fluorinated organic byproducts are formed during incineration. So incineration of PFAS is the focus of ongoing research at the US EPA and also in our research lab in Sweden and other research labs in Sweden. This is an interesting but worrying case study of what happens to PTFE coatings on commercial baking trays. The PTFE is removed and recoated after 12 to 24 months. In Sweden alone, for example, every year, approximately 20,000 baking pans are recoated with a total baking surface of 500,000 meters squared. The old coating is removed by burning off at 450 degrees for 4.5 hours or by water blasting the PTFE off the pans. These processes result in emissions of PFAS, but the releases are largely unknown. So are there alternatives to fluoropolymers? In many use cases, there may well be, but this requires detailed evaluation. For example, in the case of non-stick cookware, ceramic non-stick, cast iron, enameled cast iron, carbon steel, and stainless steel alternatives exist. Now, there are pros and cons with all of these, of course, and these need to be evaluated by alternatives assessment. Now, there may be some uses where alternatives to fluoropolymers are not yet available. These are the so-called essential uses. Now, these could include certain medical devices, for example. As I said earlier, the fluorochemical and plastics industry are keen to see a growth in fluoropolymers, and so there is a strong marketing of the properties and benefits of fluoropolymers with little effort to point out any of the problems. If we have to keep on using fluoropolymers in society for certain applications, can they be made without the hazardous fluorinated processing aids? The answer is likely yes. Arkema and Solvay, which are major manufacturers of fluoropolymers, now make fine powder PVDF without fluorinated processing aids. They previously used the ammonium salt of perfluorononoic acid, or PFNA, or salts of PFOA. It took about 20 years of R&D to develop these non-fluorinated alternatives. Patents are also available for making fine powder PTFE without fluorinated processing aids, but these have not been operationalized to date. But with some years of R&D, fine powder PTFE can certainly be made with non-fluorinated processing aids. It just requires an incentive by the manufacturers. So now to conclude and come up with some ideas for the way forward. So are fluoropolymers polymers of low concern? Well, the answer is no. Environmental releases of PFAS occur during their life cycles. The use phase may be relatively safe, but large amounts of PFAS are released during manufacturing and at the end of life. PFAS-free alternatives exist for some uses of fluoropolymers, and therefore substitution is possible. If we need fluoropolymers for some applications, we must improve manufacturing and waste management of fluoropolymers. This is certainly possible, and pressure needs to be applied to the manufacturers. Finally, thank you for your attention, and I look forward to the discussion. I would also like to thank my co-authors from the Global PFAS Science Panel and the Tides Foundation for the funding.
Hello, Ian, and thank you.
Hello, yes, I went for a shorter presentation, but hopefully there's lots of good questions coming.
Yeah, we certainly have enough time now to finish this part of the session and take the time to discuss questions related to Ian's talk. Do you want to go ahead, Jitka, again?
I can first start here with the questions from audience, if there are any. It seems that everybody is waiting for the panel discussion with the questions. So maybe you can start with the question from the WUA.
Yeah, they are on. Do you see them, Ian? I'm not sure exactly who sees what here.
Yeah, I can see the questions. Yeah.
There's one.
How often are they present in the final product?
Yeah.
Yeah, well, they are present and measurable, and it depends on the product, but and where the product is made. So how much effort they take in removing them. But in the paper I mentioned, they looked at some of the fluoropolymer products which are made by some of the companies in like, for example, the Fluoro Council group of companies, and they have made efforts. For example, if you buy a PTFE cooking utensil these days, efforts would have been made during the manufacturing process to make sure that there's very low residuals in that product. So historically, there may have been high levels of residuals in some of these products, but these modern products have very low residuals, and this is used then. This is how they argue then to motivate that these are fluoropolymers are substances or polymers of low concern because they are fairly, pure polymer products that don't have many impurities in them, and therefore will not lead to any exposures during or low exposures during the use phase. So you might get more PFOA from the food rather than from the pan. So that's their argument. Of course, their argument totally focuses on the use phase, and that's why in our paper we tried to point out, the actual terrible tragedies that have occurred during the manufacturing phase and are still ongoing during the manufacturing phase, a huge amount of PFAS that's emitted during that phase, and also the problems which are associated with the end of life of fluoropolymers. So so the residuals I think are pretty low. I'm not saying they're unmeasurable, but they're not going to lead to significant exposures compared to other sources, in my view.
Good, thank you. I would like to pick as the next one, if you know that, which applications use the largest amounts of fine powder PTFE?
Oh, that's a good question. I think that a lot of the uses are industrial, and so they might not be consumer products. There can be lots of tubings and pipes and so on used in lots of industrial uses. Coatings on cables and so on. But there are many uses, and I think that but there are lots of uses in consumer products as well. For example, all of us have cell phones and cars, and all of those, not just PTFE, but all of those have multiple applications of fluoropolymers in there. So the fluoropolymers, PTFE and other fluoropolymers are really widely used in society. And I think most of us are not aware of all of these uses and how widely used and how they have become such a wide part of our modern society. I'm not saying that that's good and that they can't be phased out, but they have become very much entrenched in industrial uses and consumer uses in our society. I can't recall which uses were the highest, but one surprising use of fluoropolymers, which I was surprised about, and it's not use of PTFE, but it's the use of fluoropolymers in all types, a wide range of different non-fluorinated plastics as using as molding and extrusion aids. So you will find a lot of fluoropolymer processing aids used in non-fluorinated plastics, and I think this is one of the biggest uses of fluoropolymers. So when you measure you try and use these total fluorine methods to measure fluorine in plastic materials, you'll find fluorine in there because of the fluoropolymers that are added as extrusion and molding aids in these plastics. And so this can be a problem in food packaging, where you use total fluorine as a method for sort of like determining whether PFAS are in your food packaging or not, because the plastic materials will contain fluorine because they've been added to improve the molding and extrusion of the plastics.
Yep, thank you. I would like to pick one more question before we may turn to the audience. That is by Mark Steiner, which is, even if PTFE or PVDF was produced without PFAS polymer processing aids, aren't the manufacturing side products still classified as PFAS? So other oligomers or other...
Yeah, there would be some for sure.
Side products.
So that's an issue that doesn't go away, I guess. You would get rid of a lot of additional... I think it would be an improvement for sure. So like some companies, like I mentioned, Arkema, have moved to totally non-fluorinated processing aids. And I'm not sure if anyone's done any monitoring around these sites to actually determine if there's still fluorinated byproducts coming from there. But I would expect there would be some. There'd be a lot of the sort of because there were also a lot of impurities in the processing aids, I think, so that were associated with that as well. So those would go. But you would get a lot of other probably low molecular weight PFAS, and that's a really interesting question. And I don't think it's been explored, because I think Arkema, I don't think anyone's done any monitoring around their plant in France. Would be interesting to do so.
I agree. That would be an interesting point. So now we may turn to the audience. Yitka, if you have something.
I believe we have one question from Emily Donovan. Yeah.
Hi, Ian. Thank you so much. Who ultimately gets to decide what low concern is? I'm assuming it's a regulatory agency, but scientific community and industry going back and forth, at some point someone has to decide that. And then the second question I have is, do we know what the body burden is of background levels just in everybody's blood and how that impacts low concern?
Yeah, the first question maybe is the easiest one, because I think it's not just regulators that are responsible. I mean, regulators I think, have a big responsibility in deciding whether fluoropolymers need to be regulated together with the PFAS, and whether polymers need to get more attention, because they've been traditionally been regulated separately from the low molecular weight organic substances, and so so I think regulators have a part, but I've also seen that consumers and product manufacturers are also playing a very big role. We had a seminar on PTFE cooking utensils, and in Sweden, a lot of the retailers who are making PTFE cooking utensils, who have made them historically, are now looking for alternatives and are actually trying to phase out PTFE cooking utensils. So that in Sweden, there's a retailer called Servia, and they've got a big campaign going right now to try and phase out PTFE cooking utensils. And also then consumers become more aware of the issues as well. Well, they can make consumer choices. So I think there's lots of different actors who can have an influence on phasing out fluoropolymers. So I think regulators, product manufacturers, and even the chemical manufacturers are making changes, at least. Even if they're not phasing out fluoropolymers, they are trying to make them in more responsible ways. So it's got. I agree that Gen X is not really an improvement on PFOA, but the non-fluorinated processing aids, I think, are a better step. And they're trying to do more recycling, although I really doubt they'd say that. I really doubt whether they're going to really do much recycling. And then because it's just so expensive to do the recycling, like with lots of other plastics, to remove them from these complicated consumer products. Regarding the second question was about the levels in blood. What could you repeat that again? Because I kind of got a bit focused on answering the first question there.
Yeah. So the second question is: we know that 99% of human blood, American blood, has PFAS in it. So there's a baseline level of body burden we can assume reasonably. Then when we come to the understanding of what is low concern, do we factor in global contamination of human body burden, things like that?
Yeah. I'm not sure if I fully understand this question, but it is a global. I think when you look at what's in human blood, 99. I don't like that 99.7. That's another thing. I think it's in everyone's blood. It's just like a detection limit, a statistical thing where they say 99.7. But what level is of concern, I think, is changing all the time, and you can see that with the drinking water sort of guidelines that have gone down for PFOA. I think they've changed. I think there was a paper by Gloria Post that said that they've actually changed by several orders of magnitude in the last 20 years. So what's the sort of like level of concern has changed totally as we understand more and more about these substances. And I think that's the problem with these persistent substances is that you have extremely persistent exposure, right? So and if you continually release them into the environment, those levels will gradually increase. So you can never be sure that you're at a safe level, because you always might discover something about the effects that's going to make you think, oh shit, the the safe level has to drop down a bit further. And then actually, if you realize that, there's very little you can do to actually reverse the contamination with these very persistent chemicals. So you can't take the chemicals away from the environment or exposure media. So you've got a really big problem there for a long time into the future.
It seems that we have a comment on this question from Dr. Slit, so please.
Hi, I just wanted to draw the audience, in particular to Gloria's question, that on the 6th in the afternoon when we have our our biomedical toxicology section, that Dr. El Katten is giving a final talk, and his expertise is actually from the pharmaceutical industry and using physiochemical properties for classifications and specifically for predicting clearance, hepatic and renal clearance. And just to tune into that talk, because he'll be going through a lot of the strategies that they use in big pharma to take their libraries and do predictive work about the kind of question that Gloria had. So I just wanted to point out that to the audience.
Thank you. We might have one more question before we move to the break and to the panel discussion afterwards.
Thank you. This has been really great. Something I've been curious as a woman, we've seen a few papers showing PFAS in cosmetics. I think lipsticks particularly, that we eat our lipsticks essentially. We wear lipstick and eat food, but other things touching our skin. And the papers I've seen, no one calls out the brands, so we know which brands we might want to avoid. And I don't know if it was Elsie last night talking about that soon we're going to be notified. We'll know what is in the different kinds of consumer products like cosmetics. And so just want to see if you can comment on that in particular.
Yeah, I can answer. I think we're getting a little bit beyond my subject, but the PTFE is used in a lot of cosmetics. It's one of the most common PFAS that you find in a lot of cosmetics. But I think what you can do is you can look for the brands which say they're not using PFAS, because there are quite a lot of brands that have come out and said that they're going to phase out PFAS. I think there was like 7 retailers or something that last year, a couple of years ago, said, right, we're not. We've known for quite some time that PFAS were in cosmetics, even though this paper that came out recently got a lot of publicity. There were old papers that have been published that showed this a few years ago, that PFAS was in cosmetics. So it's not news for us researchers that are in the field. And there are a wide range of different kinds of PFAS that are used in cosmetics. As I say, PTFE is one of the common, and they're going to be probably, I think it's low-hanging fruit in terms of they will be phased out by a lot of product manufacturers. But in the meantime, definitely buy those products from those manufacturers who have said they're phasing out PFAS. And so there are a lot of retailers who are responsible, are going to quickly phase out PFAS from their products.
Thank you. Sorry, I'm not sure if Rainer, I thought that Rainer might have some comments, but we are actually on time, so I think that we will take a 10-minute break now, and we will be back in 11:40 our time for the panel discussion. Thank you very much.
Very good. Thank you.